All right, chapter number 3, we're going to start focusing on the makeup of the atom. And when we start focusing on the makeup of the atom, what we're specifically going to be doing is we're going to be looking at that structure of the atom. And more specifically, this section, we're going to be looking and comparing and contrasting those 3 subatomic particles that make up an atom. Again, if we think back to what John Dalton talked about, again, remember we talked about his hypothesis and what specifically he thought the atom was. The one main thing on what he thought the atom was he thought it was going to be this hard, dense sphere that was going to be completely uniform throughout. Now, when we go ahead and we start talking about his model of the atom, really remember what we said. His was going to be that shot put looking shape. So again, his model of the atom would have just been a solid circular structure. Again, nothing special about it. And like I said, the main thing to think about is it really was going to end up looking like a shot put. In 1897, J.J. Thomson comes along. And the thing is, he found out that this atom wasn't completely uniform throughout. He found out that there were going to be 2 subatomic particles. The very first one that he found out was the electron, and that electron is negatively charged. And the second one that he found was, again, knowing an atom was electrically neutral, he found that there was this positively charged particle, and that positively charged particle he ended up calling a proton. His model of the atom, well, specifically it was called the plum pudding model. But really what it was this. We've got this circular atom, and again what he said was there's going to be this completely positively charged filling in the middle. Okay, a lot of positive completely spread throughout. But then what he noticed or said was, well, there's going to be these electrons that are just going to be spread throughout the atom. Again, plum pudding model. A lot of positive filling here, and then again these electrons are going to be spread throughout. Now, more specifically today, it's sometimes called the chocolate chip cookie dough. Again, for any of you who have made chocolate chip cookies, again, you've kind of got that yellowish looking dough batter. And again, that's going to be the positive. But once you add that bag of chocolate chip cookies to that dough, each little chocolate chip would represent an electron. So when you take a spoonful of chocolate chip cookie dough out, all of that yellow would represent the positive, and then all of those negatives or all of those chocolate chips would represent the negatives. So plum pudding model or chocolate chip cookie dough. In 1911, Lord Rutherford comes along, and again, he did this gold foil experiment. Again, we still have the protons and electrons, but he found something specific about those protons. If we go ahead and look at this particle emitter and this gold foil experiment, well, the key thing to know here with this gold foil experiment was that particle emitter there. The key thing about that was this was positively charged. Okay? And here's the thing, if you follow that ray along, that ray hits this gold foil, but if you look, most of that ray goes straight through. Okay, I've got 3 particles up here that are kind of deflected off, 3 particles here deflected off, and I actually have 2 particles that are actually reflected backwards. Well, what he said is we need to look specifically within that atom. And again, if you remember what I said, each of these is going to be positively charged. Each of those rays is positively charged. And again, if you follow this top one along, okay, it's coming kind of towards the center of that circle and gets deflected off just a little bit. Follow this second one here, it goes straight through. Follow the third one here, it goes straight through. Follow the fourth one, heads right at the center of the circle and actually bounces back. And the thing is, we know that the only thing, and Rutherford knew, the only thing that's going to cause something to move or something to bounce back is if it has a large positive charge and is going to be extremely massive. So instead of the plum pudding model like Thomson said, where those positives are completely spread out, he said that those positives had to be packed in the middle. So again, Lord Rutherford was able to conclude 2 things. Number one, most of the atom's empty space. And again, that's the reason why most of those particles went straight through. The second thing he found out was instead of those positives being completely spread out, he said that they were going to be packed in the middle. So he said that that atom had a dense positive core. So his model of the atom is going to look like this. So again, we're going to have our circular structure here, but we're going to have a small center. And with that small center, that's going to be the center of the atom that had just those protons in it. And he said, okay, Now these electrons are just going to be spread throughout. Okay, so again, very similar to what Thomson did, but instead of it being spread out, again, now he just went ahead and placed it in the middle. And the thing is, one thing that you're going to definitely need to know is basically each of these models, and you also need to make sure you know the scientist involved with each of these models. As we continue along, 1913, so only a couple of years went by. And the thing is, Niels Bohr knew that these charged particles had to be moving. What do I mean by that? Well, again, if I have a negative here and a positive here, and they're just sitting there, we know that opposites attract. And again, if, like what Rutherford said, the positive is sitting here in the nucleus, and we have these negatives sitting on the outside, what's going to keep that atom from imploding on itself? What's going to keep them from coming together? And the only thing that's going to keep them from coming together is if those negatively charged particles or those electrons were moving. So his model of the atom now looked like this. So again, we're still going to have those protons in the middle, but what he said now was this. Those electrons on the outside were going to be moving. Okay, so each of these is going to be the negatives on the outside. Still have the positives in the middle. Okay, still going to have those positives located right here in the center, but he now had these electrons moving around the outside. Our current atomic model, there was one more piece of the puzzle. The last piece of the puzzle ended up being found by an individual by the name of Chadwick. And again, what he did was he said, okay, we have another particle. It's neutrally charged. It helps make up a lot of the mass of the atom. And again, it was him, and there were some others involved, and we'll talk more about them in chemistry, but there was a lot of other scientists that found that these negatively charged particles, or those electrons, had different amounts of energy, had different levels of energy. And like I said, there was still another piece of the puzzle that ended up being found. But again, where those electrons are, those different levels, they ended up calling those orbitals, designated energy levels for the electron. So what our current model of the atom is this. We have the center of the atom that has protons. It also has neutrons. On the outside, we have an electron there. We have an electron there. We have an electron there. And I'm not going to draw them all out. I mean, I've got 3 levels going around here, but in reality, there ends up being 7 total rings or orbitals that end up going around that nucleus of the atom or around that center. But we have our protons and neutrons in the middle. And the thing is, that middle also, that middle is going to be called the nucleus. And where these electrons are on the outside, as I just got done saying, those are going to end up being your orbitals. Okay, so you're going to need to know that current model of the atom, protons, neutrons, in the center called the nucleus. On the outside, those orbitals, that's where you're going to find your electrons. So what's in an atom? Okay, an atom is going to be made up of 3 subatomic particles, really, that we've already discussed. Number 1, that's going to be the proton, a positively charged particle, and you've already seen some of my shorthand. It's going to be represented by P positive. Second one is the electron. It's a negatively charged particle, designated by E minus. And the last one is that neutron, a neutrally charged particle, or N0. The nucleus, that's that center of the atom that holds the protons and the neutrons. The thing that I also want to tell you about the nucleus, this is where all of your mass is. Okay, electrons do weigh something, but technically not very much. It's your protons and neutrons that are the massive ones. And then those electrons, they're going to be moving on the outside or around the nucleus in that area that we called orbitals or energy levels. And again, what keeps the atom together? It's really going to be held together because those electrons are negatively charged and those protons are going to be positively charged. Opposites attract, but again, that atom doesn't implode because those electrons are moving around the outside.
Each atom has a center called a nucleus. Compared to the entire atom, the nucleus is very small. How small? Well, chemists suggest that to imagine the size of a tiny nucleus in an atom, we think of a marble in a large football stadium, like the one we see here. In turn, an atom's very tiny nucleus contains two major particles, a proton and a neutron. Protons are positively charged particles located in the nucleus, while neutrons are electrically neutral. All protons are identical, and all neutrons are identical. Surrounding the nucleus in an atom is mostly empty space. But here, moving around the nucleus, we find negatively charged particles, named electrons. These three tiny particles, the proton, neutron, and electron, that are part of every atom, are called subatomic particles. A proton and neutron have about the same mass, both very small. But an electron is still far smaller. Scientists tell us that the mass of an electron is only 1/2000th of a proton or neutron. But chemists say that despite this difference in mass, the positive electrical charge of a proton is equal to the negative charge of an electron.
In the early 20th century, scientists continued to forge ahead in their exploration of the micro-universe of matter. Striving to understand the particles that make up matter, the Danish physicist Niels Bohr developed a planetary model of the atom in 1913. Given this perspective, the planets circling the sun in the solar system serve as a model for the subatomic particles in an atom. So in every atom, we have protons and neutrons in the nucleus, and electrons moving around the nucleus. The electrons, however, don't move in fixed paths, and they circle the nucleus billions of times every second. Whirling around the nucleus, the electrons move in paths that are arranged in energy levels, with the lowest energy electrons found near the nucleus, and the higher energy electrons circling farther from the atom's center. We know that atoms are different depending on the elements they're part of, and that all protons are identical, as are all neutrons. Considering these facts, then, what do you think distinguishes one atom from another?
The distinguishing factor lies in the particles in a nucleus, or more specifically, in the number of protons that exist in the nucleus. For instance, take the atom of carbon, which has 6 protons in its nucleus. A dark solid, carbon makes up most of the burned wood we see here. While on the other hand, nitrogen, with 7 protons, has just 1 more proton than carbon. And nitrogen is a colorless gas that's all around us, making up most of the Earth's atmosphere. So the number of protons in a nucleus determines what the element is, whether it's carbon or nitrogen, or perhaps aluminum or gold. Each atom, then, has what chemists call an atomic number, which refers to the number of protons in the nucleus. The concept of an atomic number was first developed in the early 20th century by a British chemist, Henry Moseley, who used X-rays to differentiate the nucleus of different elements.
Let's take a look at this chart. The element carbon, for example, has 6 protons, thus giving it an atomic number of 6. And the element helium has an atomic number of 2. So the number of protons in its nucleus would be 2. The model for atomic numbers also takes into account the number of electrons in an atom, reasoning that since atoms are electrically neutral, the number of electrons in an atom will be equal to the number of protons. Let's look again at the carbon atom, where the atomic number is 6, which indicates that the number of protons in the nucleus and the number of electrons in orbit around the nucleus are both 6. Now consider this. If the element aluminum has an atomic number of 13, how many protons and electrons does an atom of aluminum contain? Remember, because an atom of aluminum is electrically neutral, it must contain exactly the same number of electrons as protons. That is, 13 electrons and 13 protons.
So what makes gold different from silver? Again, the number of protons in the nucleus of an atom determines the chemical identity of the element. The atomic number, that's the number of protons in the nucleus of an atom. Because an atom is electrically neutral, for this chapter and this chapter only, this is also going to be the number of electrons. So when you look at a periodic table, and again, every periodic table is going to have this information. Okay, here's our element name. Here's our element symbol. Again, very similar to the ones that you had to know for me. But when you look at a periodic table, everyone's going to have this whole number, and there's also going to be this number down here, this decimal one, that's called the atomic mass. But we're going to focus on the atomic number. When I look at helium, its atomic number is 2, meaning that it has 2 protons, and it's also going to have 2 electrons because, again, it's going to be electrically neutral. The atomic number tells you the protons and the electrons. If we go ahead and look at how many protons and electrons are in copper. So again, if you go to the periodic table, find copper, you look at that whole number. The whole number on copper is 29. So that means that it's going to have 29 protons and 29 electrons. On the flip side, I can go ahead and ask you, well, which element has 74 protons? So again, go to the periodic table. The protons tell you the chemical identity of the element because you look for that atomic number. Finding number 74 on the periodic table, you're going to get tungsten. If we go ahead and look at the mass of an atom, again, most of the mass of the atom, as I've already said, comes from the nucleus of an atom. And again, that nucleus has your protons and your neutrons. Electrons are extremely small. It takes about 2,000 electrons to equal the mass of 1 proton. That'd be like a person stepping on a scale and they weigh 150 pounds. Well, that scale is going to read 150 pounds. Well, now what I'm going to do is I'm going to give them a paper clip. And I'm going to say, step right back on that scale. And the scale is still going to read 150 because, again, we know that a paperclip weighs something. We know it has a mass. But it is so small that it's almost going to be negligible. And that's what really the electrons are. But again, what we're right now focusing on is the protons and neutrons. We're focusing on the nucleus. And that means the mass number. The mass number is the total number of protons and neutrons in an atom. Okay? It's the total number of protons and neutrons in an atom. So what we're saying is mass number is going to be equal to the protons plus the neutrons. There's different kinds of potassium. Okay? It's actually been found that there are 3 different kinds of potassium. There's K39, K40, and K41. This 39, 40, and 41, those represent the mass number for each of those potassiums. This one has a mass number of 39. This one has a mass number of 40, and this one has a mass number of 41. So if we go ahead and look, we look potassium up on the periodic table, we find its atomic number. That means that it has 19 protons. Each one of these is potassium. That's why I have 19 written down on all of them. Because an atom is electrically neutral, that's why we also write down 19 electrons. 19 electrons and 19 electrons. Notice 1919, 1919, and 1919. But what about the number of neutrons? Well, to find the number of neutrons, we're just going to rearrange. The number of neutrons is, take your mass number, subtract away your atomic number. So on this one, here's my mass number, 39. We're going to subtract away the atomic number. 39 minus 19, we get 20. This one here, we're going to take 40 minus 19. This one here, we're going to take 41 minus 19. And when I do that, here's my neutrons. Notice, what's the same about each element? Protons and electrons are the same. What's the only difference? The difference is going to be the number of neutrons. It's potassium on all 3. And if it's potassium on all three, that's why we have 19 protons, 19 electrons. It's our neutrons that are going to be different, and it's found by taking the number of neutrons to get mass number minus atomic number. It says determine the number of protons, electrons, and neutrons in gold. So first thing you're going to do is notice a mass number is not given. So what you need to do is you need to go to the periodic table, look it up, and round that atomic mass to the nearest whole number. When I go to the periodic table and I look up gold, I find out that it has an atomic mass, okay, that decimal number of 196.967. So what I'm going to tell you is if a mass number is not given to you, go to the periodic table, look at that atomic mass, round it to the nearest whole number. And if we go ahead and round it to the nearest whole number, that's going to help us find our answer. So, again, finding it, atomic number, 79. Electrons, because again, it's electrically neutral, 79. My neutrons, again, that 196.967, I said round it to its nearest whole number, so I'm going to round it to 197. I'm going to subtract away that atomic number, 79. 197 minus 79 gives me 118. So 79 protons, 79 electrons, 118 neutrons. So a little bit in review. Okay. If we go ahead and look at the subatomic particle, we can find its charge, mass, and location. For protons, protons are positively charged, and we're going to say essentially they have a mass of 1. It's located in the nucleus of an atom. Electrons. Electrons are negatively charged. Again, I said they're about 2,000 times smaller. In reality, it's 1,840. Okay, so it's 1 divided by 1,840, and again, it's going to be found in those orbitals or energy levels. And the last one, neutrons. Neutrons have no charge, but again, they're equal in size to the proton, so that's why essentially we say they're 1, and they're also going to be found in the nucleus.